Higgs boson,
चंद्रशेखर लिमिट,
string theory,
न्यूट्रिनोस,
quantum entanglement.
कुछ समझा क्या?
Ever felt bored and confused while reading lengthy physics textbooks or articles?
Yeah, on God, bro.
I'm Arnav,
And I'm Pratham.
and welcome to Quark Talk, where we decode all the complexities and simplify these intricate concepts in physics.
They may have seemed too complex to understand until now.
So, Pratham, ever feel like there's something in the room with you but you can't see it? And I'm not talking about short people.
Bro, are we starting a new series of ghost stories? Because I didn't sign up for all of this.
Nope, not ghosts either. It's something way spookier. Dark matter. Scientists think that it makes up about 85% of all matter in the universe, but no one's actually seen it. This is part 2 where we are diving even deeper into the mystery of dark matter, why it might exist, and what's been around so far.
Wait. So we're talking about something that supposedly exists everywhere, but it's completely invisible. I mean, that sounds like my motivation to study.
Pretty much. But seriously, it could be shaping the universe as we know it. Imagine a shadow universe that's 5 times more massive than everything we can see, just floating around us, completely undetectable, except for the way it affects gravity.
Okay, but if we've never seen it, how do we know it's even there? What's stopping scientists from just making all of this stuff up?
Good question. Let's rewind to 1933 when Swiss astronomer Fritz Zwicky, that's a kind of a tongue twister.
But you still said it right for the most part, though.
So Fritz Zwicky, Z and Z in the end, okay? So he was studying a cluster of galaxies called the Coma cluster. He expected to see the galaxies orbiting in a way that matched the visible mass. Obviously, right? That's what a normal person would expect.
Of course.
Instead, they were moving way faster than they should have been, as if something unseen was pulling them inward. He called this invisible force Dunkel Materie, or dark matter.
So basically, galaxies were acting like they had way more mass than what we could see.
Exactly. But back then, no one really took him seriously. And 40 years later, Vera Rubin and Kent Ford were studying the rotation speeds of stars in the Andromeda galaxy. Normally, the farther you go from the center of the galaxy, the slower things should orbit. Kind of like how planets in our solar system work. But nope, the stars way out on the edges were moving just as fast as the ones near the center.
That's like if Pluto was zooming around the sun as fast as Mercury. That'd be wild.
Yeah, exactly. The only way to explain it was that there had to be a ton of invisible matter spread throughout the galaxy. And later, with radio telescopes, astronomers found that even gas cars orbiting galaxies were moving too fast. All these signs pointed to one thing: dark matter.
So we know it's there because of how it affects gravity. But has anyone actually detected it directly?
Well, that's where it gets tricky. There have been over 50 experiments that have tried to detect dark matter particles, but only one of them have found anything. And that's Dama Libra, not Dark Libra. Dama Libra. It's deep under a mountain in Italy, and it's basically a dark matter detector.
But who names these things? Doesn't it sound like some rejected Italian opera?
Dama Libra, I know, right? But this experiment has been running for 20 plus years, so it's kind of not rejected Italian opera. It's like a nice going Italian opera.
Don't overanalyze, please.
So it's been picking up a strange signal every year, where the number of detection peaks in June and drops in November. Some scientists think that this could be the first direct evidence of dark matter.
But why would dark matter behave like it's following some school calendar?
I mean, it's not, but it could be because of Earth's movement through the galaxy. Our solar system is already zipping through space at 220 kilometers per second. And that's right, I said second, not kilometers per hour.
Of course.
So, on top of that, Earth orbits the sun at around 30 kilometers per second. So for half the year, we're moving with the sun, plowing faster through dark matter, if it exists. And the other half, we're moving slower. So if it's real, we should see more of it in June when we are moving fastest and less in November when we are the slowest.
That's actually pretty cool. But is the Dama Libra experiment the only one that actually sees the signal?
Well, that's a problem, right? Because other similar experiments haven't detected anything, which makes scientists very skeptical. So to check if this effect is real, they're working on an identical experiment in a gold mine in Australia. Your favorite place, Australia, hometown?
Of course, why not?
University of Sydney.
Yeah.
So since the seasons are reversed in the southern hemisphere, but our motion through dark matter stays the same because we are still on Earth, if they see the same results, that's a big win for dark matter enthusiasts.
But what if Dama Libra results are just because of something boring like temperature changes or even More tourist activity.
I mean, exactly right. That's why they need more experiments to confirm. But dark matter isn't the only explanation for these weird galaxy movements. Some scientists, or you can say conspiracy theorists, maybe like them think that maybe gravity itself needs a rewrite.
Oh, great. So now we're questioning gravity. What's next? The moon is actually made up of cheese or what?
Nah, it's made of iron. Okay, so whatever. So some physicists propose MOND, okay? It's called Modified Newtonian Dynamics. So instead of saying there's invisible matter, they just suggest that gravity behaves differently at very large distances.
So instead of dark matter, they're saying our equations for gravity are just plain wrong.
Yeah, plain long, especially at large distances.
Okay.
And this idea explains galaxy rotation curves without needing extra mass. Like, no dark matter, basically. But the majority of scientists still lean toward dark matter existing because of something called the bullet cluster.
Sounds like a cool name for a band, doesn't it?
It's like one of the coolest names for anything we've heard ever, like for any science-related thing. Like,
That's true.
Dama Libra, bro, that's not a cool thing.
That's not it at all.
So, the bullet cluster is basically a collision between two galaxy clusters. So when they crashed, most of the visible matter, which was hot gas, slowed down and got stuck in the middle. But when scientists mapped where the gravity was strongest using gravitational lensing, they found that most of the mass wasn't where the gas was. It just passed right through, exactly like dark matter would.
So if Mond was right, gravity should have been the strongest in the middle.
Exactly. And the bullet cluster is one of the strongest pieces of evidence that dark matter is real and not just a side product of gravity.
Right, and even more evidence for dark matter comes from the oldest light in the universe. About 380,000 years after the Big Bang, light could finally travel freely throughout space. This light, which we see today as the cosmic microwave background, which we've talked about before,
Yep.
it gives us a glimpse of what the universe looked like back then, like a lot of years ago. And it shows us clues about dark matter's role in shaping the cosmos.
So there are like some red spots where that show the early universe was just a little bit hotter, and the blue spots show where it was just a little bit cooler. But these differences were like very tiny because I think 0.01% tiny, but they're there. They're not negligible, but they're there.
And you can turn this picture into a graph by counting up how many blobs there are of different sizes. There's the most common size blob, which results in this peak. But there are also other common size blobs. So you get these other peaks of decreasing size.
And the height of those peaks that you're talking about depends on how much dark matter there is, right?
Exactly. In a universe without dark matter, the graph looks different. But as dark matter increases, the amplitudes of even-numbered peaks decrease. To match the measurements of the CMB, we need about 5 times as much dark matter as ordinary matter.
And this figure of 5 agrees with how much dark matter we need to explain the motion of stars and galaxies and the motion of galaxies and clusters. So the dark matter hypothesis actually makes sense. It explains a lot with a simple framework, but what is it exactly?
It's basically something that we have theorized because our calculations don't work, okay? So we've got galaxy rotations, bullet cluster, and possibly Dama Libra. We're still not exactly sure what this dark matter is, but the leading theory suggests that it is made up of some unknown particles. These particles barely interact with normal matter, only influencing it through gravity somehow. And scientists are actively searching for these particles in underground labs, particle accelerators, and even deep space.
So basically you're on the hunt for invisible particles that don't want to be found.
Exactly. It's trying to catch a ghost. It's like trying to catch a ghost with a butterfly net. But if we do manage to find them, it could revolutionize our understanding of the universe.
Yeah, and the million-dollar question is, as you said, what is dark matter, right? Since we don't know, they've proposed a bunch of different possibilities and now we have to go and try to find them.
Different dark matter detection experiments look for different types of particles, right?
Yep, Dama Libra. So annoying to say it. Like, it's fine, but Dama Libra and the detector at the bottom of the gold mine in Australia are looking for WIMPs. Weekly. Okay. Diary of a Wimpy Kid.
Yeah.
So WIMPs are weakly interacting massive particles. So these particles are expected to weigh about as much as a proton, which is I think 1.008 something 1.007 atomic mass units. Whatever, don't need to know that, but they weigh as much as a proton but interact with ordinary matter extremely weakly.
How do they even detect something that barely interacts?
Well, the core of the detector consists of seven kilogram crystals of pure sodium iodide. The idea is that very rarely a dark matter particle might hit a nucleus in the crystal and transfer its energy. Although it's like very less, but it's there, right? And that energy will create a flash of light called a scintillation. And then there are these things called photomultiplier tubes, which are extremely sensitive light detectors to pick up those very, very, very short and weak light flashes called scintillations.
So we're basically just using so many fancy words to summarize detection, okay?
Yeah, you're detecting a very weak particle hitting a crystal that is emitting a very, very, very faint like light ray called scintillation using photomultiplier tubes, which are just light detectors which are very, very sensitive. That's it.
But isn't there a ton of background noise that could actually mess with the experiment?
Good, very good question, right? Because even the purest sodium iodide crystals contain radioactive potassium, which emits electrons and gamma rays when it decays. And these events could just look like dark matter for us, right? To eliminate them, the crystals are submerged in a tank filled with 12 tons of linear alkyl benzene. It's a liquid scintillator that emits light when exposed to a gamma ray. And this allows scientists to filter out false positives. So, like, basically, we figured out a way to not to ignore background radiation and all that stuff.
But what about cosmic rays? Aren't these things everywhere?
Well, another great point, but energetic particles from the sun and distant galaxies like Earth hit Earth's atmosphere, creating muons. And these are essentially heavy electrons that travel close to the speed of light. And they also create flashes of light in the detector. And to avoid that, we just simply keep them underground. That's it.
So the deeper the detector, the fewer the muons, and that's better.
Yeah, exactly. At the surface, muon detectors pick up a few hits every second, but 1 kilometer underground, the number drops by a factor of a million. So, that's why these experiments take place in old mines like that gold mine in Australia.
So even if we're doing it underground, wouldn't like radioactive elements in rocks mess with the experiment?
That's another problem. So the mine walls contain trace amounts of uranium and thorium and like a bunch of other radioactive materials, right? Like everything, it can contain anything. And they decay into radon gas, which is a big problem for these experiments. So as humans, ingenuity is unparalleled. They've found a solution for that as well. So the cavern walls are coated with a special paint to contain those radioactive particles. And those crystals are also immersed in a continuous stream of pure nitrogen gas. And the entire detector is shielded by 120 tons of steel and plastic.
That's some serious protection. But what if they find nothing?
Well, if they see nothing, then that will be the death of Dama Libra. Like, it's rejected. The soap opera, Italian soap opera is rejected. And it's never going to come back. And it's a loss of a lot of money. But if we see something, it could be groundbreaking. Literally.
Oh, but actually, if we see something, we could maybe think that dark matter is just more than a particle. Like, what about an entire dark version of the standard model itself?
Yeah, like a particle, antiparticle, but a dark particle.
Version,
exactly.
Yeah.
Nice. That's one possibility, right? Or there could even be multiple types of dark matter, just like we have protons, neutrons, electrons. Or it could be even something stranger. Like we do literally have something called a strange particle. Like this strange pattern. Strange quark, exactly. Strange quarks exist, okay? So, yeah.
But just imagine, what if dark matter doesn't interact with ordinary matter at all?
And that would make things way, way harder. If dark matter and normal matter never interact except through gravity, then detecting it might be just close to impossible.
So if dark matter is real, we might one day find it. And if it's not, then?
Then we'll have to rethink everything we thought and everything we thought we knew about the universe, except either way we are pushing the boundaries of knowledge, so that's what matters, right?
Yeah, isn't that what science is all about?
And if anyone sees any invisible particles floating around, let us know.